So I'm Segal. I'm a PhD student at Yale, and this is joint work with Professors Bryan and Joan Feigenbaum. So to do a quick overview, I'm going to start by reviewing the current state of affairs when it comes to mass surveillance and privacy. Then I'll present our privacy principles for open surveillance processes. We'll do a case study into the case of the high country Bandits and present a lawful intersection protocol that realizes our privacy principles. And finally, I'll talk briefly about an implementation of that protocol and an evaluation of its feasibility and running time. So first of all, the current state of the art in the discussion on surveillance and privacy is that the government performs secret surveillance and secret data collection, founded in secret laws or secret interpretations of laws, overseen by secret courts, stored in secret data centers for secret investigations, and using secret methods. The only information that is actually put out is that the public should trust that the government is doing something lawful and righteous with this private data that they're looking at. And often in support of this request for trust, it's often put forth that there's an absolute trade-off between national security and personal privacy, where if we want to have security, we need surveillance, and that means that we can't expect any privacy at all. Now, on the other hand, it seems like if that's true, then the ideal for free and open communication would be a world with no surveillance at all. But we think that that is a bit too much. It's a bit unrealistic. Law enforcement and intelligence agencies have been and currently are active in every national and global scale mass communication system, and we don't believe the internet is going to be an exception to this. But the Snowden revelations may have provided an opportunity for a more realistic goal, which would be surveillance with privacy protection. This may sound like an oxymoron, but we don't believe it is, because we don't believe that there is an absolute trade-off between national security and personal privacy. There's no need to abandon privacy. We can have national security while we can have personal privacy while meeting national security goals by relying, instead of trust in the government, on cryptographic technology that will protect the privacy of some of the users whose privacy ought to be protected while meeting the needs of law enforcement and national security. And we can also replace trust by replacing secret processes for data collection with open processes for data collection. So by open processes, we mean processes whose technical details are made public. In addition, that must be founded in the rules and procedures of public law. So they do not have to disclose the targets and details of investigations, but they should be open in the general way in which an investigation can be run, technically and legally. We also want privacy-protecting surveillance or privacy-preserving surveillance to distinguish between two types of users, targeted and untargeted users. Targeted users would be the people whose information we want for law enforcement purposes the government to actually collect. These would be people who are under suspicion of committing a crime, the subjects of properly valid warrants based on probable cause, but whose identities may be known or unknown. So a targeted user could be suspect John Q. Smith. It could be the person who robbed this bank. It could be a person who's planning on building a bomb, and so forth. By contrast, we want untargeted users, or people whose information ought not to be collected. And this is the vast majority of people on the internet. These are people who there's no cause to suspect them in a crime. They are not the known or unknown targets of any investigation. They're simply people whose information happens to be in the same data set as the information of someone who is under suspicion. Now, currently, there is no distinction drawn between these two types of users whatsoever, at least as far as we know. What goes on is similar to the graphic on the left, where all sorts of information from the government is ingested in bulk into government surveillance processes, which are completely secret, and we have no idea what happens inside that cloud of secrecy. All we know is that they're collecting as much data as they can about whoever. So to replace this, we would like to see a basic openness principle that we're calling an open privacy firewall. And it consists of two main planks. The first of which is that any surveillance or law enforcement process that touches private information about untargeted users must be an open and public, unclassified process. And the second is that any secret surveillance process, if a secret surveillance process is necessary, any secret process must use only public information and private information about targeted users that was obtained via an authorized warrant, via an open surveillance process. So the reason we think of it as being like a firewall is that these investigations can still take place, but the data they use must have come through an open process, an open legal process, before it's allowed to be used as part of an investigation. We have 4 more sub-principles to this. For a truly open surveillance process, we need division of trust, so that no one agency or no small group of colluding agencies can compromise the privacy of users on their own. We want an enforced scope limiting mechanism, so that an overly broad group of users is not captured. For example, targeted users can't be defined by whoever is doing the surveillance as the population of San Diego or the leaders or members of some ethnic or religious group. This needs to be enforced both in law and enforceable in the protocol itself. We also want there to be a finite and reasonable amount of time during which the information that a user's data was collected can remain sealed, after which the users must be notified that their information was collected. And finally, we want accountability, by which we mean statistics that are presented to oversight authorities, to the public, on how often surveillance is used, how many requests are done for information, how many people's information was collected, how much data was collected, of what type, so forth. And if a protocol meets our main surveillance privacy principle of the open privacy firewall and these 4 principles, then we'll call it an open process. And we'll come back to these principles after we've done our case study. So the case study I want to talk about is the case of the High Country Bandits. This was a 2010 case when there were a string of bank robberies in Arizona and Colorado. And the way the FBI eventually eventually solved this crime is by doing an intersection attack, by which we mean they compared several lists of data and looked for commonalities. The lists of data they compared are cell tower dumps, lists of information from cell phone towers listing all of the phone numbers that were active in range of tower X at time T. So in order to solve this case, the FBI looked at lists of phone numbers that were active near each of these banks at the times they were robbed. And sure enough, they found only one phone number in 150,000 phone numbers that was active at all 3 banks at the times they were robbed, and that led them to an arrest. But in collecting this data, they made no distinction between targeted and untargeted users. So they also collected the information of 149,999 innocent users. And they collected that, and we don't really know what they did with it. So to make it a little bit more general, we're talking about this would be the same principle for any collection of metadata, where the goal of law enforcement is to find a targeted but unknown user whose phone number or metadata appears in the intersection of several lists. And this was used by the FBI in the High Country Bandits case, but it's also been used by the NSA in the Co-Traveler program, where instead of looking for people who were at banks when they were robbed, they'd be looking for people who were at locations where a known suspect appeared. But it's the same principle, and our protocol that I'm going to present would be used in all 3 cases. So the non-privacy preserving, non-open variant of the protocol would simply be to look at these 3 lists of information and go through and pick out anything that appears in all 3 lists, which would be that one number. Now in this case, that one number would be the targeted user's information, the only data that the government ought to collect. The rest of these numbers, the government should have no right to look at in plain text. So our privacy protecting solution to this protocol, to this problem, is based on a paper by Feigenbaum and Clifton in 2005. And it's a private set intersection protocol that is built to satisfy our surveillance privacy principles and distinguish between the information of targeted and untargeted users. And we rely on multiple independent agencies to execute this protocol, and that will give us division of trust, accountability, and so forth. An example of what I mean by multiple independent agencies could be one agency from each branch of government, like an executive agency such as the FBI or NSA, a judicial agency, which would be a warrant issuing court that's actually part of the judicial branch, and a legislative agency, which doesn't necessarily have to mean a group of senators, but more like an oversight committee established by law. And it doesn't have to be something exactly like this, but the point is that these are independent agencies that we're expecting not to collude with one another in violation of the protocol. So I'll go through the protocol itself. It's based on commutative encryption schemes, which simply means an encryption scheme where the same data encrypted under multiple ciphertexts, under multiple keys, that ciphertext can be decrypted under the decryption keys, but in any order. So the order of encryption and decryption does not matter. So we can think about encrypting under a commutative encryption scheme as applying a layer of encryption, which other layers of encryption can be added or removed in any order. So each agency will have an encryption key based on a commutative public key randomized encryption scheme. Meanwhile, the sources of phone metadata, which are telecommunications companies, in this case, would encrypt each data item using the keys of all agencies and give these encrypted sets to some kind of repositories. And the question of who exactly the repositories are is important but a bit orthogonal to this discussion, so we're not going to get into it. But when the agencies have agreed on a legal warrant for intersection, then they give the warrant to the repositories who would validate it, and the repositories would distribute encrypted data sets to the agencies. And at this time, the agencies would also select temporary keys for a deterministic commutative encryption scheme that will be used for this one intersection and then securely deleted. So I have an animation here, and in this animation, the numbers in the middle are plain text that have been hidden by layers of encryption, as I mentioned before. And these ciphertexts are represented by the different colors. So you see each of these colors are different. So it's 6 different ciphertexts in 3 lists. And the point of this protocol will be to find any numbers that appear in all 3 lists. So each agency will start with these data sets. And each agency in the first phase of this 3-phase protocol will just decrypt each item using its key for the randomized encryption scheme, removing a layer of encryption, so to speak, and encrypt the ciphertext again using its key for the deterministic encryption scheme, which would add a layer of encryption back. And then it will permute each set and send it to the next agency, which will do the same thing, decrypting using a randomized encryption scheme and encrypting using a deterministic encryption scheme. Now in this example, we have only 2 agencies, but there could be more, so they would continue doing this until every agency has encrypted. And the data is now not protected by any layers of randomized encryption, it's only under deterministic encryption. And when the same plain text is encrypted under deterministic encryption, it will have the same ciphertext. So phase 2 of the protocol is simply looking at each of these lists of ciphertexts and finding any ciphertexts that appear in all lists. So unlike the earlier plain text case, anything that does not appear in all 3 lists is not revealed to the government. And in fact, anything that does not appear in all of the lists that we're comparing, that data will be deleted, and any agency that sees that data in the future will not operate on it. It will never be decrypted. The only thing that will be decrypted is the intersection, the commonalities between the 3 lists, which in this case is just this one ciphertext. Now it's possible that this is an example with 2 entries per list, but with very large entries per list, there could be many ciphertexts. We won't know until this step in the protocol, but we could have a lot of ciphertexts. And if any agency sees that there are more ciphertexts than expected, then that agency can stop the protocol unilaterally. And the point of this is to provide scope limiting. As for our concert scenario, where unknown to the FBI in advance, there's some band that's been touring and giving concerts in the same cities as these banks are located. And to compute this intersection would reveal the information of a lot of people who have been to each of these concerts and guilty of no other crime. So if any agency sees, hey, there's too much information that's about to be released here, it can stop the protocol by deleting its key, its temporary key, and nothing will be revealed until a more precise warrant can be determined. But supposing that we are going to complete the protocol and reveal the one or however small intersection, the last phase of the protocol looks a lot like the first. Each agency uses its temporary key for the deterministic crypto system to decrypt, removing a layer of encryption. It permutes the set and then passes it on to the next agency, which decrypts using its temporary key until the plain text is revealed. At which point the final results are sent to all participants, and the temporary keys are securely deleted. So nothing but this intersection is revealed. So let's go back and compare this to our privacy principles. First of all, this does satisfy our main principle of being an open process. It distinguishes between targeted and untargeted users by revealing the information of the targeted user, the presumed bandit, to the FBI or whoever is running this protocol, while protecting all of the information of the non-targeted users using encryption. And furthermore, we can openly standardize this protocol and the crypto behind it without compromising the investigative power at all, making it a lot more palatable to law enforcement agencies. It also satisfies division of trust. No one agency, and in fact, no set of agencies, fewer than all of them, can perform this protocol or decrypt on its own. Scope limiting is enforced by the fact that any agency can stop this protocol if it notices that the initial sets are larger than expected or the intersection is larger than expected. Sealing time and notification, we can implement this by policy, and the reason that's doable is because all agencies see the final data set, so they can be responsible for notification. And by the same token, accountability is guaranteed by the fact that every agency must participate in this protocol, so that no other agencies can perform this attack in secret. So every agency is responsible for collecting information about how often this protocol is run, how many people's data was revealed. They can always collect this information and present it to the legislature, to the public, to everyone who needs to know about it. Okay, and I'll take a few minutes to talk about our implementation of the protocol. So we implemented this lawful set intersection protocol in Java. We tested it with 3 agencies, run on Planet Lab nodes distributed across the United States in Connecticut, Texas, and California. And we just did a proof of concept implementation, but it's available on GitHub. And the GitHub link is in the paper as well. And the results are right here on the right. Our main result seems to be that the running time increases linearly, or the running time increases by a linear amount with each added data item, roughly 130 to 150 milliseconds per item of metadata per set. So for an example, the size of the real-life high country bandits case, the end-to-end running time for the entire protocol was just under 2 hours. And we think that this is actually very reasonable. And there are 2 reasons for this. First of all, considering the time it takes to get warrants, it would take the FBI 2 hours to do anything anyway. And for a law enforcement process, 2 hours is not bad at all. But second of all, as I mentioned, this is just a proof of concept work. We used an unoptimized crypto library in Java that I wrote myself. And we use only one single threaded worker per agency, in spite of the fact that this is an embarrassingly parallelizable problem. So there's a lot of room for improvement on this running time. So the fact that it's 2 hours with this unoptimized implementation, we think shows that our idea of using privacy protecting protocols can actually be very feasible. To conclude, our main point is that open surveillance processes can and should be designed to meet law enforcement needs while protecting privacy of untargeted users. We believe that privacy protecting surveillance is not an oxymoron, but it is in fact feasible using existing encryption technology. And for future work, we may be interested in testing our protocol with an optimized multi-threaded implementation, or in creating privacy-protecting protocols to replace other forms of surveillance, such as keyword search, like the NSA's PRISM program, or contact chaining, where anyone who is 2 calls away in the phone network from a suspect's information is collected, even if they are really an untargeted user. And so we may look into privacy-preserving protocols to replace those forms of surveillance. And finally, we're interested in testing with general-purpose secure multi-party computation platforms like Fairplay and ShareMind. And what these would do for us is they would let us automatically compile a surveillance query that would not necessarily be privacy-protecting into a protocol that is privacy-protecting and secure in an automatic way, without the author of the code for this protocol knowing anything about cryptography. We don't know how feasible these systems are in terms of the running time, so investigating that will be another direction for future research. Right, and thank you very much. Here's some bandits.
So two questions come immediately to mind. One is, I assume that the basic protocol can't handle things like you're looking for Joseph Philip Schlabatnik, but you have databases with Joey Schlabatnik and JP Schlabatnik and Joseph the Shiv Schlabatnik, and I assume that that's not going to work here. You don't have wildcards. You can't handle misspellings and things. I can just imagine that the law enforcement side of things is not going to go for something where that's where they're so dependent on the exact same spelling of everything in each database. And then I forget what the other one was, but
well, and that's true. This protocol would not work if the data does not start out exactly the same in plain text. I think the question of how to standardize data is probably not insurmountable, especially when it comes to metadata like phone numbers. But even in general, I think if there's some agreement that these data sets will all use full first name, full last name, then this would work fairly easily. I should point out that this protocol is not meant to replace PRISM or something like that. This is meant to replace metadata that comes from telecommunications companies.
So yeah, this is a related question. So we did some work where we were looking at underground forums and trying to match people up, and we found that one thing that we could use a lot was ICQ numbers, but we found sometimes the two guys were trying to use the same ICQ number, and then it was pretty simple. But often it was the case where they used the same, they both used the ICQ number of this third person, and it turned out all three were connected and so on and things like that. Or you might actually know that this person has 3 different cell phones and so the question is, do you think it's possible, is it the case that you just have to use straight up SMC to deal with this sort of thing in this way, or are there ways to extend the work that you're doing to do something that's maybe a little lighter weight, do you think?
So the question was, is there a way to handle cases where some people have multiple
cell phones, or they're shared with, or there's this case where these 2 people actually share with a third person? You can imagine a bandit ring where not every bandit is present in every location, but there's a threshold of them. So there are a lot of these kind of cases which are,
Right.
which are expansions on the idea and maybe aren't a whole other, don't require a fully general solution, but maybe. But I can see again it being an implementation adoption hurdle for law enforcement who will clearly have dealt with a lot of these types of scenarios.
It could be. It would be straightforward to move from a case where the same ciphertext has to appear in all sets to some sort of algorithm where the same 3 ciphertexts have at least 2 members in each set. That would be a straightforward modification.
In fact, the protocol already basically does
The protocol basically does that.
There's a stage where you can just see, this phone number appears in 2 out of the 3 sets. Okay, is that good enough? And does the resulting set still satisfy our threshold of safeguards? And you could actually, so we actually discussed this. That's in some sense, at least from a theoretical perspective, an information leakage. If you're, so this isn't a perfect private set intersection protocol. If your goal is to is to get only the pure, K of K threshold and leak nothing else. This does not, strictly leak nothing else. But on the other hand, what it does leak actually does give you, a little bit more flexibility if you're, interested in also to kind of address Paul's point, I think there's a lot of interesting kind of potential work beyond this into figuring out how to deal with approximate. What is a good way of dealing with kind of approximate queries too? I see at least 2 avenues. One is is just to kind of normalize, Soundex code the names, into a few kind of normalized variants before they go under encryption. That you could probably get some mileage that way. Another way would be to use, slightly more fancy but similar kind of homomorphic encryption techniques, where you just kind of, under encryption compare some attributes and then sum the, under encryption sum the number of, the matching score or something, and then out comes and then we decrypt the ones that have a sufficient matching score. You can see how, but that's all totally future work, of course.
Another, I thought of my other question, which was, is there another generalization? Is it okay if I need to hop? If I could imagine scenarios where you have this separation of duties thing going on, but for various policy reasons or whatever that like one or more of the agencies, presumably not all of them, but one, that would be bad, but that like they're not allowed to see the result. So like, you have 3 agencies who are part of the authorization process, but one of them is not, they don't have the clearance to see the outcome of that. Could you, is that just something that because of the way your crypto is set up, you're just stuck, you can't handle it, or can you think of generalizations that might cope with that?
I think the protocol as it is, that would fall out automatically as a possible variant of that. You just have to
right, you just have to be careful in what order.
In the correct order.
Oh, okay.
Right.
Only the agency that's supposed to see it,
Yeah.
see it.
Right.
Yep.